we've talked about the different properties of gases. The important parameters are the volume, the temperature, the pressure, and the amount of gas in moles. And so to make it easier to compare gases, we have something called standard temperature and pressure, which is abbreviated STP. So for gases, we've defined standard pressure as 1 atmosphere. So that's like regular pressure, right? And for standard temperature, it's defined as 0 degrees Celsius or 273 Kelvin. Why that number? That's the freezing point of water, right? And so if you have an ice water bath and you put the gas container in it and give it a little bit of time, even without any technology, even without a thermometer, you can know that that gas is going to be at 0 degrees Celsius. And so that's the reason I made up in my mind that helps me remember that it's 0. So we can talk about the molar volume of a gas at STP. So this is the volume of 1 mole. The molar mass is the mass of a mole. The molar volume is the volume of a mole, right? So we can calculate this from the ideal gas law. So rearranging the ideal gas law to solve for volume, we get V is equal to nRT over P. So we're trying to calculate the volume of 1 mole of gas, so N is going to be 1 mole. And R is what R always is, 0.08206 liter atmospheres per mole Kelvin. And what is the temperature? Standard temperature. 273. We have to use kelvins, right? So 273 Kelvin. And then what's standard pressure? 1 atmosphere.
Because we need to cancel it out.
So, yeah, we have to have that in atmospheres. So atmospheres cancel, kelvins cancel, moles cancel. And the answer we get is 22.4 liters. So that's the volume of 1 mole of gas. And that's about the size of kind of a medium cardboard moving box, about this big. So, not a huge volume, 22.4 liters. So the molar volume of any gas at STP is 22.4.
So is that going to be our constant now?
So that is a useful conversion factor. You can only use it for gases at STP. So please don't try to use that in stoichiometry problems with liquids and stuff. It doesn't work. It's only for gases at STP. So this is 22.4 liters is 1 mole of gas. That's 6.022 times 10 to the 23rd molecules of gas. It doesn't matter what the gas is. It's going to occupy the same volume. So that's something that's sort of unique to gases. So here we have an illustration. We got a tank of helium, tank of xenon, tank of methane. And here we have 3 balloons. They are all the same volume, filled with these gases, 22.4 liters. Each of those balloons has a mole of gas in it, even though the gases are different. This is a little hard to get your head around sometimes. There is a lot of empty space between the gas particles. And so the fact that this atom or this molecule is bigger than this just doesn't matter in terms of taking up space. Now, this balloon is going to weigh a lot more because the particles weigh a lot more. But equal volumes of gases have equal moles, regardless of what the gas is. So then this is gonna sound kind of like that exam problem everybody loves to hate. Assuming ideal behavior, which of these gas samples has the greatest volume at STP? So we've got 1 gram of hydrogen, a gram of oxygen, a gram of argon. Well, let's just write down their approximate molar masses. So hydrogen is about 2 grams per mole, and oxygen is about 32, and argon is about 40. I am not using these numbers in a calculation. You should never round atomic masses to fewer than 4 sig figs. These are just to help us have relative sizes. So we have equal masses of these gases. They're asking us about the volume. Well, what's going to affect the volume of the gas? The temperature, right? But we can assume that, well, actually it says at STP. All of these gases samples are at STP, so the temperature and the pressure are the same. So what's the other variable besides volume?
The size of the element?
No, amount. The amount, the number of particles, right? The size of it is going to come into density, which is coming up very soon. So if we had more particles, we'd have more volume, right? So 1 mole of gas is going to be 22.4 liters. What's the volume of 2 moles of gas? Be 44.8. Twice as many particles, twice the volume, right? So if we're looking for the greatest volume, I want to pick the one that has the most particles.
So C, 1 gram of argon. No, you said 1.
We want the most particles.
Oh, so A, 1 gram of hydrogen.
Yeah, it's A.
How much we can see, that's the one on the test.
It's very much like the one on the test. And there might be one like that on the makeup test. Okay, so this was the analogy I came up with the other day. I'm sure we could come up with better ones. So I have a box of bowling balls. The box weighs 100 pounds. Which kind of ball would give me more balls in the box? The 10 pound, right? See, that makes sense to you. But over here, not so much, okay? So this is a smaller bowling ball, and this is a bigger bowling ball.
So basically, out of any particles we have, or any atoms that we have, the smallest one has the greatest volume. Or did I write that?
You'll have the largest number of particles
Okay.
for the mass. Yes?
If volume is the measure of space, why wouldn't it be something that's big? Like you're asking the greatest volume.
That's a great question. So why isn't it argon? Because argon atoms are much bigger than hydrogen molecules. Because a gas is mostly empty space. So we have these molecules or atoms, but in between, there's literally nothing. In a solid or a liquid, a gram of argon would take up more space because the particles are bigger and they're touchingly close. But in a gas, they are not touchingly close. They're spread out all over the place. So the size of the particles don't matter.
I'm trying to see, so if 1 gram of argon would just be one heavy particle going around in the space, or would it be?
Well, you would need fewer particles of argon to make 1 gram. Okay?
1 gram of argon isn't a particle itself?
No.
Oh.
A mole of of argon weighs 40 grams, so you'd need 1/40th of a mole, right?
And those, because of Avogadro's number,
Mm-hmm.
that's one.
Because the mole is a counting number, like a dozen. Yeah, it's easy to forget that.
And 6.022, that is one particle?
That is 1 mole of particles. Yeah. So Avogadro's number is like the 12 for dozen. 12 things is 1 dozen things. It could be chairs, it could be donuts or pencils or anything, right? A dozen just says how many of this thing. A mole does the same thing. But instead of 12, it's that really weird number, 6.022 times 10 to the 23rd. Which we use that number in the beginning of general chemistry, but we really don't use Avogadro's number much after that. But we have to understand what is a mole. It's a certain number of particles. Yeah. So here, if we have a gram of helium, that's going to have more particles in it because each of the particles weighs less. Just like with the bowling balls. If I have 100 pounds of bowling balls, didn't mean to do that, 100 pounds of bowling balls, if the box is full of 10-pound balls, I'll have 10 bowling balls, right? And if it's full of 20-pound balls, I'll have 5. Because each of the balls weighs more. So here, argon, each particle weighs more, so there's going to be fewer atoms here. The gram of argon would take up the smallest volume. And the gram of hydrogen would take up the greatest volume. And the value of questions like this is not to torture you or trip you up on an exam. It's to make sure that you understand these ideas. Because you can get good at doing calculations and stuff and not really know what you're doing, right? Okay, so density of a gas. Density is the mass divided by volume. That's the same definition that we used before. The units for gas densities are generally grams per liter instead of milliliter, just because gases are much less dense. So grams per liter gives us nicer numbers. So at STP, you can calculate the density of a gas by taking its molar mass and dividing by the molar volume. So that's great and all, but I'm against adding unnecessary equations to remember. So the way I do this, density is equal to mass divided by volume. So if we're trying to find the density at STP, we can choose the amount of gas. If I have 1 mole of gas or 5 moles of gas, does the density change? No, it doesn't. The mass changes and the volume changes, but they change proportionally. So if I have 5 times as much, then I'm going to have 5 times the mass and 5 times the volume, and those 5s are going to cancel out. Density does not depend on the size of the sample. It's the same. Just like percent composition. That other question on the exam. Mm.
Is this the multiple, what, the law of multiple proportion, or?
It kind of seems like the law of one of those laws of
Yeah.
proportions, but it isn't.
Okay.
So density is mass over volume. The size of the sample doesn't matter, so I can pick a size that's convenient. I like 1 mole. So if I choose 1 mole as my size, I'm basically going to end up with this. What's the mass of 1 mole? the molar mass. I didn't finish this. And what's the volume of 1 mole of gas at STP? 22.4. So over here, we're supposed to calculate the densities of helium and nitrogen at STP. So the density for helium, we're going to do 1 mole of gas. What's the mass of 1 mole of helium? It's in the periodic table.
4.00.
Yeah, 4.003 if we use 4 sig figs. What is the volume of 1 mole of helium? 22.4 liters. That's the volume of any gas at STP. So 0.177 grams per liter. Now, if we want to find the density of nitrogen gas, I didn't mention this with the helium, but anytime we're talking about an element, not as part of a compound, but an element by itself, we always need to ask ourselves, is this one of the diatomic elements? Is helium a diatomic element? No, the noble gases don't do stuff like that. Is nitrogen a diatomic element? Yes, it is. So then what's the formula for nitrogen gas? N2. It's not N. And this is going to have an effect on the density. So what is the mass of 1 mole of nitrogen? So it's going to be 2 times 14.01, because a molecule has 2 nitrogen atoms, right? And what's the volume? 22.4.
We can only do this when the temperature and pressure
Yeah, at STP. So this is 1.25.
And then something like the question will say, calculate for STP, or you want to be like a words problem and just say, hey, calculate this density, and without it saying like giving us like it's for ST.
It will either say at STP, or it will give you a temperature and pressure.
and it will be, that's constant, right?
So for that problem, you're just calculating the density under that set of conditions. Because if you change the pressure or the temperature, then the density is going to change.
If they give us a temperature and pressure, what's the formula for STP then?
Well, STP is when the temperature is 0 Celsius and the pressure is 1 atmosphere. And that just makes it easier to compare gases. You don't actually often have gases at STP.
0 degrees Celsius
In 1 atmosphere. Yeah. So what's normal atmospheric pressure? 1 atmosphere, right? And so then what do we think of as a normal temperature? Well, a lot of times they say 25 degrees Celsius is room temperature. It was 22.6 in here right now. 25 is a little warm if you ask me. So instead of quibbling about what room temperature is, they're doing 0, which is ice water. Okay? What am I doing? I don't even know. So what about other conditions? Well, I approach those the same way. Density is the mass divided by the volume. So if they don't specify this as the quantity, I'm just going to choose 1 mole. Now, this is an equation in your textbook. The density is equal to the pressure times the molar mass divided by RT. And that is a valid equation, but again, that's another equation to remember. And I'd rather just stick with D is M over V. So one of my students in the other section told me about a mnemonic to remember this one. Denny's is a PM restaurant. If that works for you, great, but I'm not going to use it. Calculate the density of xenon gas at a pressure of 742 millimeters mercury and a temperature of 45 degrees Celsius. We're going to have to use a gas law. So I'm just going to go ahead and do what I've been doing all semester. I'm going to highlight those numbers in yellow and highlight what I'm trying to find in green. And I see y'all doing problems in the worksheets and stuff, and sometimes needing some help and getting lost. And I'm telling you, try writing this stuff down like I'm doing in lecture. I'm not doing this because I need to write it down. I'm doing this because I have found that it really helps students. Do you always have to write stuff down for the rest of your life? No. But until you can see what's happening, it really helps to write stuff down and label things, okay? So, if you don't have highlighters, underline or circle or something. So I'm going to take these numbers out and write them down. So 742 millimeters of mercury. We're talking about gases, and it actually says that that's the pressure. And then we've got a temperature of 45 degrees Celsius. And then we're trying to find the density. So we think, well, what is density? Density is mass divided by volume. Here we are calculating the density. We have to use the density equation. So I need the mass of this gas and its volume. They're not saying how much gas there is. So I'm going to choose 1 mole because it makes things easier. So I'm going to choose 1 mole of gas. And I don't know where to write that. I'll just put it here. Choose 1 mole. I mean, you can choose any number you want, but just make it harder. What is the mass of 1 mole of xenon gas? 131.3 grams. That's why 1 mole's easy. Right? So the mass of it is just its molar mass, 131.3 grams. And now I need to find the volume. Well, I can find the volume using the ideal gas law. So I've got P and I've got T. R is always going to be the same.
The N is the 1 mole that we're talking about?
Yep.
Do we have to change the temperature to Kelvin?
We do have to change the temperature to Kelvin. And what else do we have to change?
The MM is
Yeah, the millimeters of mercury. So 1 mole is my N. So I need to change this into Kelvin, so I'm going to add 273. It's 318. And as frequently happens, do not plan ahead very well. Let's move this guy over. I don't know why I enjoy doing that so much. So converting pressure, always just 1 step. I want atmospheres because that's the unit in the ideal gas law. So multiply by atmospheres, divide by millimeters of mercury, so those units cancel out. The table given in the book with all the pressures relates everything to 1 atmosphere. 1 atmosphere is 760 millimeters of mercury. Let's move that one more time. So 0.97632 atmospheres. So now I have N, R, T, and P. I can plug them in my equation. Yeah.
I have a question.
Mhm.
Pressure is how much gas is in there pushing the xenon down?
So the pressure is what we get from the particles of the gas hitting the walls of the container. So if you think about what holds a balloon open and big, it's the pressure of the gas inside of it, right? You let the gas out, and then if the balloon is not tied, and you just let the gas out, well, now the pressure inside is the same as outside, 1 atmosphere, and the balloon's just going to be floppy and not big and round. But if I put a bunch of gas in there under pressure, then I can make the balloon stretch out and get nice and big.
And the xenon gas is at 45 degrees Celsius.
Yeah, this is saying the xenon is at 45 degrees Celsius, and the pressure of this sample of gas is 742 millimeters of mercury. Okay, so then we can plug these things in here. I've got 1 mole, and I've got R, and I've got T. Somebody squeeze them in the corner. Divided by the pressure.
You just did one wrong because it just said like the density of the xenon gas. If it had said what 2 xenon gases, then you would have done 2 mole. Like how would we?
So the density of something does not change with the sample size.
That's right. So it's always gonna be.
So I pick 1 mole because it makes the calculations easier. Yeah.
Oh.
Okay, that's the only reason. Yeah.
And a problem when they do give you the grams, will you have to convert that to moles?
No, usually the problems where they give you the mass, they're going to ask you to calculate the molar mass. There'll be something else that you don't know.
Calculate the molar mass?
Yeah, it's coming up. It's coming up. So 0.08206 times 318 divided by 0.97632. So this is 26.728 liters. So that's my volume. So I'm going to plug the volume in here. I've got 131.3 grams divided by 26.728. So this will come out to 4.91 grams per liter. If I change the temperature of the gas, or I change the pressure of the gas, the density is going to change. Because changing the pressure or the temperature is going to cause the volume to change, but it's not going to cause the mass to change.
So divided by 22.
Well, if it was STP, we'd use 22.4. This one wasn't at STP, and so we had to go do a little more work and calculate the volume.
So are we done with this?
Yes, we're done. So that's the answer up there. This is the density.
Oh.
So here's another problem. This is saying calculate the molar mass of the gas. Hang on. So I'm actually going to skip this one because when the book does it, they use that equation, the Denny's equation. And we're going to do another problem just like this in a couple slides, and so we'll just do one of them. Arrange the following gases in order of increasing density at STP. So the test bank has a lot of questions like this where they give you some things and they want you to order them. So in order of increasing means that I'm going to list the smallest thing first, the smallest density, and I'm gonna go to the biggest density at the end. Okay? So sometimes it's better not to look at the choices because they can be a little confusing. Let's just think about these gases we're dealing with here and what we can figure out. So density is the mass divided by the volume. So this is at STP. So if we calculated all these densities and said, let's use 1 mole, then the volume would be the same for all of them, right? Would the masses be the same? No. The masses of some are going to be a lot bigger than others. So if I have a big mass divided by the same volume as the other ones, then I'm going to have a bigger density. That make sense? So for my most dense gas, am I looking for the heaviest element or the lightest element? So the density is equal to the mass divided by the volume. The volumes for all of these guys are the same. But the masses are not. If I have a large mass, I'll have a larger density. So if I want the largest density, do I want the heaviest element or the lightest element? The heaviest element. It's like, well, she didn't like the other answer. We'll try the other end instead.
So density is the amount of space it takes up?
Density is the mass of it divided by the amount of space it takes up. Yeah, so the volume of 1 mole of gas is the same, regardless of what the gas is. But if the individual particles weigh more, then the density will be larger. So the density is not the same.
It'll take more room in that little 25 liter.
It won't really take more room, it'll just weigh more. So, with the one, so the 22.4 liters per mole, and I'm really glad you're asking these questions. So this is Avogadro's number of particles, right? 1 mole of particles. And if I'm looking at density, it's the mass divided by the volume, right? So the volume, if the volume's, that's 22.L. Note in it. If we're looking at 1 mole of each of these gases, they're all going to occupy the same volume. They're all going to have the same number of particles. But some of these particles are going to weigh a lot more than other particles. Like chlorine, that's a diatomic element, right? So that's about 70. Yeah, about. That one's about 70, right? Neon is about 20. Is that right? Yeah. Oxygen is about 32. And fluorine is about 38. Just 2 times the molar mass. So if I think about a dozen particles instead of a mole of particles, because somehow dozen just makes so much more sense to everybody. If I have a dozen of each of these, which sample's gonna weigh the most? The chlorine. Right? Because these particles weigh more. And so if I have equal numbers of all of them, chlorine's going to weigh the most. So which one's the most dense then? The chlorine. So we can look at our choices here, and both of these have chlorine as the most dense. This one does not, so that one must be wrong. Which of these is the lightest? Neon. So equal numbers of neon and chlorine, the neon's going to weigh less. They're taking up the same volume. So this is going to be the smallest, the least dense. So that points me to this one. And we were expecting neon and then oxygen and fluorine and chlorine. Yeah.
So density is like how I think of it as marbles. You get 3 bags of marbles and 3 different sizes of marbles, but you get it in the same size bag, but one bag way more because it has bigger marbles. Is that what it is?
That's a lot like what it is, yes. Yeah, yep. So because we can figure out the moles of a gas from its volume, pressure, and temperature, we can actually calculate the molar mass of a gas. So we'll actually be doing this in experiment 6A. We're going to take a volatile liquid, and volatile means that it evaporates easily. So if you think about, you're going to get an immunization and they rub some isopropyl alcohol on your skin, and it just evaporates really fast, right? That's a volatile liquid. It goes into the gas state very easily. So you can take a volatile liquid and heat it up until it becomes a gas. And then you can measure its temperature, its pressure, and its volume, and use the ideal gas law to calculate the number of moles. And then if you weigh it, you can find the mass. So molar mass is the mass divided by the number of moles. And so here the book is just using my method instead of the Denny's equation. So let's do an example here. A sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. So I've got all these numbers. And I want to find the molar mass. So then I'm thinking to myself, well, molar mass is equal to the mass measured in grams divided by the number of moles, right? So to calculate the molar mass, I need the mass of this gas sample, and I need to know how many moles are in it. So this is an example where they gave us the mass. They're not asking us to calculate the density, they're asking us to calculate the molar mass. They gave us the mass because we can't do it without that. So my mass is 827 milligrams. Is that in grams? No, it isn't. But we could do that little cheaty thing. Milli stands for times 10 to the minus 3. Now it's in grams. So that's the mass, right? Now we need to find the moles. Well, we've been given all these other numbers. We've got 0.270 liters. So that's the volume. It even says volume. And we have a temperature. It's 88 degrees Celsius. Can we use Celsius for gases? No, never. Let's just convert that before we forget. So 88 plus 273, 361 Kelvin. And then the pressure is 975 millimeters of mercury. We're going to have to change that one too. If you're using the ideal gas law, we have to use atmospheres. If you're using one of the simple gas laws where things are changing, then as long as both of your pressures are in the same unit, it doesn't matter.
So question, how do you kind of know like which one is the simple gas law versus, is there like how do you know that?
Well, one thing you can do is you can always use the table that I was making for the other things, right? If we make a table here, it's gonna end up looking like this. I'll start one over here, but then I'm gonna erase it. So if we start making a table, we're gonna have 0.270 liters. We're like, okay, that's the volume. And then we got our 361 Kelvin, that's temperature. And then we've got our blah, blah, blah atmospheres. That's the pressure. And there are no numbers in the second row because nothing's changing. So was that a waste of time to make the table? No, I got all my things labeled, right? So you can always just start making a table. If you end up with 2 rows, you're going to have one of those simple gas laws, like P1V1 equals P2V2. And the one you use depends on what variables you have, right? You use the one that has those variables in it. If you end up with 1 row like this, nothing's changing, that's where we're going to use the ideal gas law. So we're going to be using the ideal gas law, and you are correct. We need to convert this to atmospheres. And I'm going to write the result down here because it's going to leave me better space. So we'll start with PV equals nRT, and we'll rearrange it to find moles. So we're going to end up with N is equal to PV over RT. And again, if you need help rearranging the ideal gas law, please come and talk to me. Or if you want to know how you can do it on your calculator without rearranging anything, I can show you that too. So there's my atmospheres and my volume. And then I've got R, which just always takes up way too much space. And a temperature. Get your calculator out. A calculation like this, a lot of students get wrong because they miscommunicate with their calculator. So we want to fix problems like that right now. A common way for students to enter this is we've got this top number times this number divided by this number times this number. But that's going to get you the wrong answer. What we've got here is like A times B divided by C times D. If you do A times B divided by C times D without any parentheses, you're going to get A times B over C times D, which is not what you want. So there's a couple ways around that. Some calculators have this little button that will give you a fraction in the display, and then you can just type those numbers in so they look just like it does on your paper. That will avoid the problem. The other thing you can do is use parentheses. So if I put parentheses here, then I get the right answer. So that's just a little weirdness about calculators. But watch out for that and make sure that you can get through this one and we can all get the same answer. So 1.2829 times 0.27. I'm going to use the parentheses method. Divided by parentheses 0.08206 times 361, close the parentheses, equals. I have to make some room. So I'm getting number of moles to be 0.01169 moles. Did you get your calculator to show you that? Anybody need me to scold their calculator? I'm really good at scolding things. 6 kids. Okay. Sometimes when I'm doing a problem, I get somewhere like this and I just like, oh, did something. But we're not done yet, right? Like, wait, what were we doing? Oh yeah, we're trying to find the molar mass, right? So I need the mass, which I found over here, and I'm gonna divide by the moles, which is right here. I'm gonna change colors to make it less confusing, hopefully. And so our molar mass is going to be the mass, 827 times 10 to the minus 3 grams, divided by the number of moles. And this answer would have 3 sig figs. 70.7 grams per mole. Is that a reasonable molar mass? It is. You might be thinking, well, how do I know? Well, what's an unreasonable molar mass? How about -5? You can't have a negative molar mass. What about 0.02 grams per mole? No. Why not? Hydrogen is the smallest element, right? And that's 1 gram per mole. So it can't be less than 1. What if I get 6 times 10 to the 14th? Yeah, that's probably pretty crazy too. Yeah. But if I got, 159, yeah, could be. Okay. I mean, because if you think about it, radon is a gas, right? And radon's molar mass is 221 grams per mole. So definitely anything smaller than that is possible. Okay, any questions about this one? So here's another example, calculating the molar mass. This is more like what we'll be doing in lab. An organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and re-weighs it. Her data is given below. Calculate the molar mass of the liquid. I'm not going to highlight these because they're all just listed out there. So we're trying to calculate the molar mass, and so we ask ourselves, well, what is molar mass? It's the mass in grams divided by the number of moles. So that tells me I need to find the mass of this gas and how many moles, just like the previous problem, right? Except they didn't say here's the mass of the gas, because that's not how you weigh things in the lab, because gases don't stay on the balance very well. So here's my mass information. How can I find the mass of the gas? Subtract. I'm going to take the mass of the flask and the gas together, and I'm going to subtract the mass of the flask. So 78.416 grams minus 77.834 grams. .582 grams. So that's the mass. So I could put that up here. Now I need to find the moles. Yeah, we're going to have to convert things. So this volume is in milliliters. I need it to be in liters. If you're not sure what units you need, look at the ideal gas constant. It's liter atmosphere per mole Kelvin. Those are the units we have to use. So we could say, well, this is 213 times 10 to the minus 3 liters, 100 degrees Celsius. We have to convert this too. For the milliliters?
No, oh, I'm sorry, for temperature.
For the temperature. No, if it was Fahrenheit, then it would be.
Oh, okay.
But if it was Fahrenheit, we'd kick her out of school because she shouldn't be measuring things in Fahrenheit in the lab. shouldn't even have a Fahrenheit thermometer. 100, this one's 100.0. So the book's been kind of sloppy with the 273 or 273.15. Since this is 0.0, I want to use the 273.15. It's always okay to use that. So this is going to be 373.
When I first looked, I thought it was Fahrenheit, that's why I was thinking of the.
Yeah. Yeah. And then the pressures in torr. Torr and millimeters of mercury are exactly the same thing. And so the conversion factor is the same. 1 atmosphere is 760 torr. And why do we have two units that are exactly the same? Well, I could speculate about that, but I really don't know. Atmosphere. So we're going to use the ideal gas law to calculate the moles. So I need the pressure, 0.99211 atmospheres, and I need the volume, 213 times 10 to the minus 3 liters. And just a comment about doing the conversion this way. We use the milliliters to liters a lot, right? And so a lot of students take to just, well, I just need to move the decimal point 3 places. Well, yes, you do, but you need to move it in the right direction. And it often happens that they go in the wrong direction and things get really crazy. So this is a very fast way of doing the conversion without screwing it up. Divided by R, 0.08206 liter atmospheres per mole Kelvin times the temperature, 373.15 Kelvin. Zero point 0.0069012 moles. .3 grams per mole. Any questions?